conference. So I will talk about reversing Linux malware with Karate. And okay, who am I? My name is Sergio Martinez, and I'm known as zl0wram in the internet. I'm a security consultant at NCC Group. I try to play CTFs with the functionality team. I'm a member of the malware group, and I'm also a gopher. So I love to program in Go. And okay, Linux malware. Malware for Linux does exist. I bet you all know. And they are mainly targeted to servers and routers, usually focused on building DDoS botnets. If you don't trust me, you could ask this guy. You all know him? Better?
But has he blocked you?
Huh?
Has he blocked you?
Yeah. I didn't request access via. So, okay. I'm not an expert reverse engineer of malware. I do it for fun. So to me, the common malware reversing problems is that usually the binaries are statically linked. So they used to be pretty big. And then if you just run the automatic analysis with low, and they are usually stripped, so you don't have symbols, you don't have debug info. And when you try to reverse engineer this, you end up like Mr. Bean. It's really boring. But using Go, the binaries are even bigger, so the analysis is way slower. You still don't have symbols, and you have that Go has a big runtime, so that you can easily get lost within functions of the runtime. And it's a kind of new programming language, and it has some particular things like routines, channels, defer, slices, and so on. And they even have custom calling conventions. So on x64, they have stack-based arguments. So it's registered. So when I first saw a Go malware disassembly, I was like, what? Where I am. So I will talk about Lady Linux, which is a malware sample programmed in Go. Yay, I'm a pirate gopher. So why Lady Linux? Because malware times handed me a sample, knowing that I like to reverse engineer Linux malware, and I love to code in Go. And at the time of receiving the sample, what I knew about it? It was written in Go, it was stripped, it was compiled for x86 or 64 bits, and there was a public analysis. Dr. Webb was like a really quick analysis, I think. They cover most of the things, but I wanted to analyze it by myself, just for learning. So, having a first look, if you run the strings on the whole binary with izz, you find strings like this one, which is, if you have ever programmed in Go, this is a type definition. Type definition, okay. And it's on the raw data section. Then this is a section that I'm not used to seeing in binaries, which is called Go PCL and tag. And you have attack. At the time of seeing this, I don't know, maybe it's function name. And here we have a full path that we can know that the guy who programmed this did it on Windows, and he called this sample lady because it's right here. So from this, we know that type information is somehow available in the read-only data section. And what it seems to be method names that are stored in the Go PCL and tag, which was pretty interesting. And well, the malware author developed it on a Windows box. So having a first look, there was like 4,000 functions without names. So you can end up analyzing functions and never finding really interesting stuff. What we could do, we could find the source code, resolve them, and try to identify which package, which is the library Go, is being called. But this is really time consuming. have to guess a lot. So what am I supposed to do now? I really want to analyze this one. So we should ease the reversing process, and the first approach was to rely on signatures. So having a look at the strings, you find that which packages the malware was using. So the first thing that came to my mind was, okay, I can build a binary, made in Go, including all the packages, so I can generate signatures for all the packages that are being used in the malware, and then load them into Radare. So creating a simple hello world, porting the packages, and then generate the signatures and load them into Radare. So I can show the okay. Is it better? Okay, here it is just a program in Go with all the packages that the malware was including. This underscore thing is that you're telling him that even that I'm not using these packages, I want to include them in the binary. There are a huge amount of them. Okay, and the main function is just a return. And then the generated signatures are more or less like this, which are bit masks and some specific bytes that they should not change from functions to functions. Okay. Then, what we could see is that from the 7,000 signatures loaded, they found Radare found 3,000 matches, which is quite good. And also taking into account that we had almost 4,000 functions, so maybe most of them we have identified them. So here's a small disassembly. I don't know if you can see it well. So after applying the signatures, we can see that we have some comments here that is saying that it's the runtime.makeChild function, which is from the runtime. And this can be enabled by using the eval bar called asm.cm2refs that shows the flag and comments from the references in the disassembly. And there was also some offsets here that I didn't know what they were about, but they are doing like a loading these others based on the RIPH register. I was like, what is this? So first approach was, let's take a look. So we have some kind of structure we can see doing this hexagon. Maybe that this 08 and 08 is some kind of size. But well, after checking empirically what could be this, I found that doing a hexagon on this offset led to this to the following one. We have two pieces here, another offset and what can be a size. So another hexagon revealed that there was actually a tag definition. So this was pretty interesting and happened with most of the offsets that I found there. So these are nice results. With signatures, it was definitely easier to reverse engineer, but I still didn't know why those strings were there, even on a string binary. So it might be runtime stuff, might be for the reflection package. Well, I didn't know, so I do a little research. And I say research because I just tried to see what it was behind that. And just when I was looking here and there in Google and things, Albert sent me a link to a tweet from Tim Strasser that said something about the Golang Loader Assist module I was working on really seems to pay off. I was like, what the fuck? He did something with the Golang samples. And then this guy called George Zates said, hey, the Golang allows even restoring original function names. And it was, whoa, I like it. So this script was for IDA, or IDA Python, and it allowed to extract the information stored in the Go PCLN tab, but there was no type information. And I interchanged some tweets with them, and they were trying to look at this. So I kept digging a little bit, and I eventually realized that all the type information was stored in a section called type link. Again, had some stuff to research maybe. So what I did is I ported the script to extract information from the Go PCLN tab to r2con, and then I developed another script to extract the type information from the type link section. And here's more or less the output. I have them running now because I have to reboot my laptop. Second. Okay, the first one. Oh no, you don't see anything. Okay, so for the type references, it loaded 2,000 and a half type references, and the function it is still working, and I don't think it will finish, but it will be like 8,000 function names. Read a lot. Yeah, 8,400. You can find the scripts available on my GitHub. So what? The reverse engineering with reverse engineering script Go binaries, you can do it like if they were never stripped, you can actually restore all the information. So you have the functions identified from the runtime, even the custom ones. Then you have the type information, so you know that you are creating a channel with type structure minor d. So now it was really easy to analyze the sample. Even Radari recognized the local variables. So this is the before. This is the after, so looks better. And there's still more work to do because I did this in the last 2 weeks. And well, I need to do a deeper research looking at the Go source, so I can really find how they are handling this information, because maybe I'm doing silly things for loading it, and it can be done more efficiently. And I also have to check which Go versions work this, because I tested it only with the 1.6, and the last one was the 1.7, if I recall correctly. So the point of this is that I wanted to analyze this latent Linux sample. So here's the actual analysis. The sample accepts flags, and these are the 4 that it is expecting, one of them. So you have the PID, the version, install, and D. The PID will accept an integer, and it looks for a process running with this number as their PID, and it exits with a 0 or 1 depending on if it was found or not. The version just print the version of the malware. Then the install just was the function in charge of the persistence. So first it checked if the procs have exe directory were pointing to the user as being NCP, which is the path and name that it was expected to be running as. If not, it will copy itself to that path, and then it will create init.d script or systemd service file in order to achieve persistence, and then it will restart the service. So the malware will be already installed. So we can see here the example of the systemd service file, in which it will be running the sample with the -d parameter, and then we have the restart always. So for some reason the malware stops running, it will be restarted. Then going to the -d parameter, it generated some processes, was Go routines in this case, and we could they were calling them IP rule, update, attack, and minor D. So, as I said, a -D flag was in charge of running the main payloads, created the coroutines, and then it would obtain metrics about the infected machine using a library available in GitHub that's called GoPSUtil. And the information that will load would be that one in the struct in the code. And my information, just the hostname, uptime, the platform, the OS. Then it would send GET request to the CNC server with the metrics in order to receive the configuration file. The configuration file is composed of multiple items that will be splitted and sent via channels to the corresponding coroutine. So here's the config file that it downloaded. The URLs are censored. I will go step by step with it now. So the IP role coroutine was in charge of obtaining the external IP of the infected machine that it will be used later in the attack coroutine. The update was simply in charge of updating the binary in case there was a new version. So if the variable version is different than the actual version of the binary, it will just get the URL, download, copy it to the user sbin ntp path, and restart the service. Then the attack is actually the propagation of the sample. I think that the sample is prepared to have more than one attack, but they have only implemented this one called Redis. And to propagate the malware, it will use the external IP of the infected machine to generate random IPs. And then it will try to connect to the Redis port, the common one. I think it was the 6.2, I don't remember now. And then we'll try to launch these commands, and we'll stop it will disable the stop writes on digit error. So some error, of course, it won't stop writing. It will remove the compression. First, it will set the working directory to /var/s2/cron, and then inside this folder, it will create a file called root with a crontab syntax that is saying that each minute it will try to download this pm.sh file and will run it. Then it will just change the working directory to the .ssh folder, and it will create an authorized keys file with a public key that is hard-coded into the malware. And then it will just somehow restore the configuration that it changed in the beginning. So first going to the file that is downloaded, it's this script. But what it will do is to override the crontab information with a similar command, because this file that has like some different number is actually the same as this one. Then if the file in the .ssh folder called kh something is not present, what it will do, it will try to create the .ssh folder in case it's not existing. It will remove the authorized keys file because he put a public key that was hard-coded in the binary, and then it will load a new public key file on this KHK75 file. It will change the configuration of the SSH service to permit the root login, to allow the public key authentication, and to include this new file as authorized keys file. And then it will restart the service. Despite doing that, okay, it was more script. Okay, it just will try to download the suitable malware compiled version for the current platform, and then we'll try to install it. And finally, it will start the new install service, and then try to then remove and kill the processes that were running from the cron contact. And then once the malware has written the public key and run this script, it will also try to connect via SSH to the target machine, because you remember that it put a public key file and it has a private key file stored. And then it will try to execute this command that will download this script that we talked about, that in fact it will remove the public key. So actually you cannot try to find which servers has compromised using the stored private key that it has. So then there's this minor D, which is the minor D coroutine, which is in charge of the monetization of the malware. It is actually downloading a binary that will be mining this cryptocurrency called Monero. I didn't know about it. So we have the piece of config about the minor D, which we can find the URL to the mining binary, and then some array of parameters that will be used to run this